If you're dealing with a force that's changing or varying, and you're in AP Physics C, then consider this. How do you know your force is changing? Think of, might be sand falling out of a container onto an object, in which case the work is probably perpendicular. Or maybe you're pushing a box through sand, and as you push, the sand is building up behind it, so you're needing to increase the more force as you go a further distance. Any of those types of situations. There's also another really big clue for when to use calculus on your AP Physics C exam, and that is in AP Physics 1, we would be given forces 32 newtons. That's it, just a number. Whereas in AP Physics C, you'll be given force as a function, which may be 32x squared. Sometimes that function will be a little bit more difficult to see. You might get a function that's just f equals x. That's still a valid function. You can still plot that on a graph and still get a line. It's just that whenever you have that function, you're going to need to, for this instance, integrate with respect to your position. And that's true for anything, really. Whenever you're given a variable as a function, you might see it f of x equals, but you'll probably just see it f equals x. Just be aware that that means you need to use calculus. Kinetic energy is the energy of motion. If you're moving, you've got kinetic energy. Kinetic energy is scalar, but unlike work, it cannot be negative. The v is squared, the speed is squared, or the velocity is squared, so it can never be a negative value. To calculate kinetic energy, you can use speed or velocity because it's squared, so direction doesn't really matter. The work energy theorem says the net work done on an object equals its change in energy, which also equals F times d. So here's that bridge happening again. We can see this change in energy. And if it's kinetic energy, delta K equals Fd. So 1/2 mvf squared minus 1/2 mv naught squared equals Fd. Very useful equation. You're not going to be given a mass and a velocity and asked what is the kinetic energy. You should be able to know how to represent changes in energy with energy bar charts. And we've worked with those throughout the year. What else do we have? I think that's it for now. Work, and then total mechanical energy. And depending on your object, let's say it's a pendulum. When the pendulum is at this point right here, all of our energy is in gravitational potential energy. So our total energy equals gravitational potential energy. If we have our pendulum here at equilibrium, then all of our energy is kinetic energy because this is the lowest point it's going to go. So I'm going to set my y equals 0 right there. On to potential energy. Oh, remember this work term can be negative. So if there's friction acting on this pendulum, we might have some negative work, which is going to decrease our total mechanical energy. If this was 2 and this is 1, or negative 1, then our total energy is just going to be 1 joule left in the system. Potential energy is stored energy in a system due to position. When dealing with an object hanging vertically from a spring, it's easiest to consider the spring-earth object system because in order to have gravitational potential energy, we need to include a reference height, and Earth is usually a really good reference height. The potential energy of the spring-earth system is 1/2 kx squared, where x is measured from the position the object would hang in equilibrium. So when we have a mass hanging from a spring, if that mass is not moving, then this is the mass equilibrium point. Meanwhile, the spring was probably this long at its natural length. When we added the mass, it stretched the spring, storing elastic potential energy. Whenever we're working with gravitational potential energy, and you see, or you're using little g means you're near the surface of the planet or the Earth. Remember that just like we did up in the pendulum situation, I set y equals 0 to the lowest point. You also get that freedom. You get to determine where h equals 0. It's usually most useful to put it at its lowest point, or maybe you want to have it at its highest point. A reference height must be included in the system for an object to have gravitational potential energy. If I am holding, an object, like a marker, right here, what kind of energy is in the marker system? No energy. Even if I have it right here. Because I have not included the Earth in my system, so there's no reference height, so there's no gravitational potential energy. Why would it fall then? Because in that case, Earth is external to the system. So the Earth's gravity is going to do work on the marker and add energy into the system in the form of kinetic energy. In the absence of non-conservative forces, mechanical energy will always be conserved. That's our total energy in the beginning equals our total energy in the end. I don't know why I drew epsilon there, sorry. If energy is removed from the system, then we would use, again, negative work. So you could even include a work term in your conservation of energy formula. So if we started with gravitational potential energy and some kinetic energy in the beginning, then in the end we have only kinetic energy because there was some work done by an external force. I could just include that work term there, remembering when to use positive and negative work. From here I could solve for work when I bring this over, when I bring the k over, and then plug in my information that I know. Conservative forces are the forces that have an associated potential energy with them. The two we know about are gravitational potential energy and the weight force, and spring potential energy and the spring force. If an object is losing kinetic energy and a conservative force is involved, the velocity is in the opposite direction of the conservative force. This is a really specific scenario, but it came up in class and enough people missed it and had questions about it that I wanted to include it. So basically what it's saying is if I throw an object directly up in the air, the speed is slowing down. So that means my kinetic energy is decreasing as it goes up. So what direction is my conservative force acting? My conservative force, not you, Fg, is acting in the down direction. Meanwhile, the velocity is up. So my conservative force is acting in the opposite direction, which results in a loss in kinetic energy. That's all that means. The slope of a potential energy versus x graph is going to be a conservative force. For those of you in calculus, you may see graphs that look like this, and you have to determine where is the maximum kinetic energy. Let me try to make it a little bit better. There we go. So where's the maximum kinetic energy? The way we will read this is if this is 5 joules at the very top, then this is maximum potential energy. At the very bottom, when there is 0 joules of potential energy, then that was going to be where our maximum kinetic energy would be. So the total energy here is going to add up to be 5. So my kinetic energy might be doing something similar, but in the opposite direction. or it might not be. Our spring force equals negative kx. Remember that negative indicates a force acting in the opposite direction of your displacement. Springs in series. It hasn't come up often enough for me to spend class time on this. And it's easy enough to where I can just go through it here quickly with you. So, if we have spring 1, which I'll use green, and then spring 2, connected like this, where they're stacked on top of each other, we would call this being in series. If you're familiar with circuits, this is just like in series. If you can imagine this is a wire, the current only has one direction to go, and that is down through the coils or up through the coils. So in series, they're stacked on top of each other. These two springs acting together would act as one really big spring with some different spring constant. The way you determine that spring constant of the total spring, we'll call that the effective spring constant when you combine these two. Our effective spring constant here can't be found real easily. We're going to take the inverse of our effective spring constant, and we'll take the inverse of K1 plus the inverse of K2. As an example, let's say spring 1 has a K of 2, spring 2 has a K of 3. To find my effective spring constant here, it's going to be 2 to the negative 1 plus 3 to the negative 1. When I add those together, I'm going to get, well, let me do this. Might be easier to see. Now when I add these two fractions together, this is going to be 3/6 plus 2/6 equals 5/6. My answer is not 5/6 because my effective spring constant has to be flipped again. So I'm going to flip that, and I'm going to say my effective spring constant here is 6/5. If you are familiar with circuits, especially capacitors, maybe you're in the engineering class or have taken some other physics that has dealt with capacitors, these springs act like capacitors. When capacitors are in series, you have to take the inverse of 1 plus the inverse of 2 to get the answer, and then inverse that answer. Probably where you'll mess up, this is easy enough, but probably where you'll mess up is not flipping it one last time. If you're interested for the why, we can talk about that. If we have springs, leave a comment below of your questions that are connected like this. We would call this being in parallel. They're side by side with one another. In this instance, to get our effective spring constant, we're going to take K1 plus K2, and that's it. Nice and easy. So in this case, using those same two spring constants, our effective spring constant is just 6. And units. Newtons per meter. If an object has a height, instantly think gravitational potential energy. If it has a speed or it's moving, think about kinetic energy. I would prefer that you would think about kinetic energy before you think about kinematics, just because kinetic energy is a lot more useful and is more broadly applied. Kinematics, you have that constraint of needing acceleration or force to be constant. No constraint in using kinetic energy. If you have a spring involved, think about, well, there's only two things you're going to think about: spring potential energy or the spring force. If you do have two of those indicators, height, spring, or speed, in the same situation, do yourself a favor and use conservation of energy first. For a pendulum, if we have a pendulum length L, and this could be a physical pendulum, it could be a mass on a string, it could be a human attached to a bungee cord, which is attached to a helicopter. It could be anything. If there's a mass at the end of a string or a rope or a cord, it's a pendulum. If we have the length of this pendulum to be L, and the pendulum makes this angle here, theta, as it swings up, our length does not change. So how much gravitational potential energy do we have? We would have to calculate this height, this change in height right here. To calculate that change in height, we say this y equals 0. I keep going back between y and h. You should know that they're interchangeable. If that's y equals 0, and we need to figure out how much height increased, so that way we can calculate our gravitational potential energy, then what we're going to do is, I've got a thing here. Found it. So to figure out this change in height, we're going to not think about the bottom, and we're just going to look at that. And what do you know? That is a right triangle. So the adjacent side of that triangle is going to be magnitude of the hypotenuse times cosine theta. So really what we're trying to do is take this full length in black and subtract out this smaller piece in yellow. So we'll take the full length and we'll subtract out the smaller piece, and that will give us our change in height. Full length minus this gives us just this change in height that we need. There's other ways to do it. You could set h equals 0 at the top and then go through it if you're working with a Hamiltonian, but probably not. So we can have it like this, and this is a useful thing to remember. We can also factor out the L, so it's going to be L times 1 minus cosine theta. That's it. Maximum kinetic energy for an oscillating system is at the equilibrium point, while maximum potential energy is found where the object changes direction. Back to our pendulum. So if our pendulum is swinging up, this is the part where it changes direction, and then it's going to go back down. The equilibrium point is going to be at it right here. Whoa. Right here. That's the equilibrium point. As it swings through that equilibrium point, it has maximum kinetic energy. Then as it goes up, it's going to have maximum potential energy. Of course, this is true for a mass oscillating on a spring. If this is our equilibrium point, as the mass comes down further, and the spring is stretched, this is where we have our maximum spring or elastic potential energy. And then at the equilibrium point, as it passes through, that's where the maximum kinetic energy is going to be. Yes, this is true for a spring attached to a box on a horizontal surface that's frictionless. If there's friction and it's dampened, make sure you treat it properly as a force. There's our relevant equations. One thing I didn't talk about was F equals negative du dx, though we kind of did when we said u versus x is going to give us our conservative force. So that means we're going to integrate that, take the derivative of that, find the slope, because these are in fraction, as we talked about earlier, rise over run. So u over x means that we're going to take the derivative, and the derivative here is going to give us that force. Power is the rate that work is done or the rate that energy is transferred or transformed from one type to another. Instantaneous power can vary over time depending on force and velocity. So power equals work over time. That's our general equation. We're also given this on our equation sheet, and here's your derivation of it. Work equals force times displacement. So force times displacement over time is the same as force times velocity. Efficiency is just the useful energy out over the total energy in, and then multiply that fraction by, or decimal by 100. Just like we had in chemistry. Impulse and momentum. Momentum is a vector quantity that describes an object's motion. It's defined as the product of mass and velocity, as seen in our equation here. Impulse is the change in momentum caused by a force. Impulse is the change in momentum caused by a force acting over a time interval. Gravity acts from an object's center of mass. Whenever we have drawn the forces and where they act, we're always drawing them from the center. That's because gravity is going to act on your center of mass. If you were to take a long meter stick and you wanted to weigh it, if you just put the center of mass on the scale, that's going to give you your reading. If there is no net force acting on a system, then the center of mass has a constant velocity, including in collisions. So we have three center of mass equations. We have the position for center of mass, velocity for center of mass, and acceleration for center of mass, and they're all looking like the same thing. It's sigma mx over sigma m. So we're going to add up mass times position plus mass times position divided by total mass. For velocity, we're going to do mass times velocity and add them all up. This is our conservation of momentum for an inelastic collision in a different way, or in a different version. You can stretch it all out and you'll see that. And then we have acceleration for a center of mass, which is the same as our acceleration for a system, which equals sigma f over sigma m, which is Newton's second law. But sometimes you're asked to find velocity for center of mass, and I've seen students really struggle with that because they think it's an equation they haven't learned. But it is. It's right there for you. For AP Physics C, we can also use the integral version of this if we're dealing with a continuous mass with continual or a not changing linear mass density. Our linear mass density is mass over L. We're just using the lambda as our linear mass density variable. So don't let it fool you. So mass over L or mass over X, and then we can substitute that in. But anyway, so we've got our position of our center of mass equals integrating all of our positions with respect to m over all the combined mass. This r is used to combine x, y, z. So each one of these has its own x dm over your mass, total mass, integrating the mass. Nope, we're not using X. We're using Y and Z. Sorry, I'm trying to rush here. And it's causing more time. If you're confused, leave comments. I'll make another one to clear that up. In a closed isolated system, total momentum before and after an event, the momentum remains constant. Momentum is always conserved. Energy ain't. So keep that in mind. Remember, momentum is always conserved. Our relevant equations are total momentum in the beginning equals our total momentum in the end. Add up the momenta of each individual object in the beginning and each individual object in the end. use impulse to calculate changes in momentum. If we're looking for a change in velocity, but we're given a force versus time graph, we can take the area under this curve, F delta t, those two are being multiplied, and what does that equal? It equals delta p. And delta p equals m times delta v. So we can find our change in velocity. We could even use that change in velocity to find our change in kinetic energy if we wanted. So keep those things in mind. The question may be asking you to do a couple of steps. None of them are too difficult. It's just you've got to do a little bit of digging. Velocity of a system's center of mass can only change when there's an external impulse. I think we said that already. And then we should be able to analyze effects of forces acting over time intervals. Momentum is a vector, so direction matters. If an object changes direction, make sure you include the sign in your calculations. So if we have a ball hitting a wall, that ball is going to go this way, and then on the return, it's going to go this way. So in the beginning, the momentum of that ball is going to be m times v. In the end, that momentum is going to be m times vf, where vf is negative. So we can include that. Negative vf, or you can put the negative in front of the m. I don't care. And then why did it change? Because we had an impulse that acted. When I solve for the impulse, F delta t equals m negative m vf minus m v naught. This negative in front changes how you're going to handle this. So it could mess up your entire problem if you forget that negative. Somebody's going to forget the negative. And on multiple choice, the wrong answer will be there. So if you forget the negative, you're going to think, oh, I got the right answer. We have our 4 different types of collisions: elastic, inelastic, perfectly inelastic, and the explosions. Just kind of memorize this chart. Momentum is always conserved. Kinetic energy is not always conserved. It's only conserved in an elastic collision. If we have a collision between 2 objects, well, let's take that earlier collision of the ball hitting the wall. How do I know if that is an inelastic or an elastic collision? I have to take the kinetic energy of the ball in the beginning and see if it equals the kinetic energy of the ball in the end. If I had multiple objects, I would add multiple kinetic energies and see if they equal each other in the beginning and in the end. If they do, then energy is conserved and it's an elastic collision. And because our kinetic energy stays the same by definition. If our kinetic energy decreases, it's an inelastic. For the perfectly inelastic, that's where the 2 objects stick together. So your equation here is going to be m1 v1 naught plus m2 v2 naught equals our combined mass times vf. The trick there is you might forget to combine your masses. And for the explosions, kinetic energy is still conserved. Kinetic energy is not conserved because it changes. In fact, our kinetic energy is going to increase because of some potential energy being released from within the system. If it's 2 skaters with their hands pushing against each other and then they go in opposite directions, and it's potential energy of their bodies being converted into kinetic energy. If it's a firework that's moving through the air, there is potential energy and then a rapid chemical reaction that happens that sends out all the particles in different directions, increasing the total kinetic energy for the entire system. There's our relevant equations. If we're conducting experiments, try to keep it simple, but if you use the smart carts like we did in our lab, that's fine if you have to write a procedure. If you are, again, looking at multiple choice questions, smart cart's probably not going to be there. Make sure you look at all the data to make sure momentum was conserved for the entire system. And then that. Let's see. Oh, we're getting close. The net impulse is the integral of force over time. So f of t dt. We can also take dp dt. This is Isaac Newton's preferred writing of his second law. And we can also get our momentum as a function of time by integrating f dt, because impulse is change in momentum. All right. Sorry, I was trying to read ahead. You will not get a perfect score on this exam or the AP exam, so don't try. By not trying, I mean don't try to get a perfect exam. Of course, try on the exam, but be aware of bread questions and know when to move on. I used the phrase bread questions. I forget where I got it from. Some physics teacher, surely. I don't think it's owned by me. If you are at a restaurant, what's the first thing they bring you? Maybe they'll get your drinks, but they're going to bring you some kind of bread. And they bring you that bread because it's cheap and it's going to fill you up. If you're at a buffet, the bread's going to be first. You're going to fill up on that bread, and you're not going to get to the more expensive meat or the more expensive desserts. The whole idea with AP, even on your SATs, College Board, ACTs, all of that, is there are going to be these bread questions mixed in. By that, I mean they're going to take a lot of your time, and you're going to feel like you really like it, but it's wasting your time. Every second is important. Every fraction of a second is important. That's why we use 10 and not 9.8. Those fractions of a second are going to add up to give you maybe an extra minute at the end of your test. So that way you can fill in the one that you just had to randomly guess at. So if you're solving a problem and you feel like it takes you a long time, for multiple choice, if it's taking you more than 2 minutes, more than maybe 4 minutes, then you know, nope, let me mark this and come back to it. I recommend using a system to mark your questions based on how confident you are that you can get the right answer. That way, when you come back to the questions, you're going to know approximately how long it's going to take you, and is it worth your time given the amount of time that you have left. So the system that I suggest is 1 star for solvable, but it will take you some time. There's going to be some calculations involved or maybe a long derivation. 2 stars for you're not sure yet, but it feels like something you remember, but it's just not coming too quickly, so move on. Give it 2 stars, come back to it. Maybe after you've seen the test, something later on in the test is going to jog your memory and you'll be able to come back and answer it a lot quicker. If you just have no clue whatsoever, which is a thing that might happen, I wish that it doesn't happen for you, but if it does happen, give it 3 stars because you just have no clue and you're not going to waste your time on that one specific question or 3 specific questions. Hopefully not more than 3. Then, after you've gone through the exam, then you can go back and look at your stars that you need to answer. 3-star multiple choice questions. See if you can get it down to 50-50. Can you eliminate 2 of the answer choices? Usually eliminating 2 of the answer choices is pretty easily done. It's doable. If you can do that, great. If you can't do that, you should be going into the exam with a guess letter. And that guess letter needs to be the same every time you make a blind guess. If you chose A, B, C, or D, whichever one, I don't care if it's A, then every time you have to make a blind guess, you guess A. Otherwise, you're trying to hit a moving target. And statistics show that you're more likely to get a question right over a few questions if you're randomly guessing. Best case scenario, we're not guessing at all. Next best case scenario, we're able to eliminate 2 of the 4 answer choices and then make a decision from there. But be decisive. Don't spend too long on one question. Sometimes you'll have a whole paragraph to read and it's going to take you a while. The format of the test. So this is a new exam this year. We'll have to see if this pattern holds up. But typically, in previous years, what would happen is questions 1 through maybe 18 were pretty easy, giving you some confidence, and you're like, okay, I got this. I can handle this exam. I'm going to destroy it. And then you get to question 19 or so. And that's a 3-star question for you. You have no clue. And then number 20, maybe it's a 2-star question. It's going to take you some time. 21, same thing. And we kind of hit this wall where we have multiple questions in a row that we know are going to take a long amount of time. These middle questions, which I am completely blindly guessing, I have no insight to this, but I would guess 19 to maybe 30 are going to be your more difficult questions. You're going to hit a wall somewhere around 19 if you're answering from 1 to 40. Then 39 or 31 through 40 are going to be a bit easier. So my recommendation is go through 1 through 18 or 1 through 16 or 15 or whatever it works out to be. And then once you hit that wall, flip to the back of the test and work backwards. Pick up all of the easy points you can. So whatever points you don't get, you know those are you're less likely to get anyway. But if you're working your way 1 through 40 and you get to number 37 and you have 3 minutes left, that's probably not enough time for you to put some thought into those questions. So I recommend while you have the time, skip to the back, see if they're easy for you. And don't just look at one and say, nope, I don't know that one, especially for this exam for my class, because you don't know everything on this exam yet. So I would recommend looking at question 40. If that's a no, 39, 38. See if there's 3 in a row that you don't know. If there's 3 in a row, then forget it. I'm an idiot. I don't know what I'm talking about. Which could be. For the next point, when 2 quantities are multiplied in an equation like F delta T, or like M times V, or A times T, if 2 quantities are being multiplied in an equation, you can plot those quantities and get a graph. And that slope of the graph is going to, the area under the curve of that graph is going to mean something. Because we're taking this area, which is length times width, so it's force times delta T, which we know gives us delta P. In this case, this is going to be length times width. It's going to be mass times velocity, which is momentum. In this case, it's going to be acceleration times time, which we know is velocity, delta V. Don't forget about that. When quantities are being divided in an equation, then we can plot those quantities and use the slope. So if it's work over time, which turns into force times displacement over time, which equals power, maybe we're going to plot work versus time. And then the slope of that is going to give us our power. If you are asked to plot quantities and use a slope to calculate, you have a data set, and then you have to come up. This is more of an FRQ thing. I'd be interested to see if multiple choice starts showing up with some of these, because I think it's entirely possible. If you have data and you have to plot the data, then you do your plotting, and then you grab your straight edge, which should be a ruler on the AP exam. If you don't have a ruler, use a second pen, use the side of the sheet. Whatever it is, you want this line to be nice and straight. See what I'm doing here by going back and forth? Don't do that. It needs to be one straight line, just like that. That one straight line should have as many points above as it has below. This is your line of best fit. Once we create the line of best fit, we can forget about the data entirely and instead just calculate the slope of the line of best fit. On multiple choice questions, this is entirely relevant because you may be given a graph and asked to determine what is this, and you have to take the slope of the best line. And you may even have data points, and they may be expecting you to take the ending data point and subtract it from the beginning data point. That's not how you calculate the slope. Once you plot the data and get a line of best fit, the data is not useful to you. In science, we care about the trends, not the individual data points. That's why we take a lot of data so our trends are more accurate. So once we have our trend line or a line of best fit, then we are going to take 2 points from this line of best fit and calculate the slope. For an FRQ, you show this by drawing this triangle. What 2 points did you use? I used these two. This is my rise, and this is my run. What else do I say? Got off on a little tangent there. I didn't get to the point I was supposed to be making. Let's say this graph doesn't look like this. And instead, let's say our graph creates a line of best fit that looks like that. Or maybe a line of best fit that looks like this. And let's say it's a y versus t graph. First thing I would say is, do I know an equation that represents this? Maybe not. I know my y is on my y-axis, so I know y equals v naught t plus 1/2 gt squared. If I'm starting from an initial velocity of 0, then I get y equals 1/2 at squared. Oh, look at that. That's kind of y and t are together. But this is an exponential graph. So I can't easily calculate the slope of this graph. Oftentimes you'll be asked to create a line of best, or a straight line that can be used to calculate the slope of whatever. Let's say we need to use the slope to calculate acceleration of this graph. I want a straight line. That's what it's telling me. Use the slope to calculate. That means you want a straight line. To get a straight line, right now we're going to use our straight line equation, y equals mx plus b. Our original equation, let's see if we can get this. Y equals, we want acceleration to be our m, so we have 1/2 a. On the x-axis, we should plot t squared, and our y-intercept will be our initial velocity times time. Well, if we don't have an initial velocity, we don't have a y-intercept, so we don't care. So, well, our y-intercept is 0, not that we don't have one. So what we end up with is this y equals 1/2 at squared. So if I were to plot not y versus t, but instead y versus t squared, that's going to give me my straight line data. All I did is take my equation and line it up with my straight line equation formula, y equals mx plus b. An alternative method you could do this if you need to solve for acceleration and you've come to this equation is you can just solve for acceleration. You're going to get acceleration equals 2y divided by t squared. So to get the slope of a graph, I'm going to plot y versus t squared. This is my rise. This is my run. Because it's a fraction, I can plot those two things. Maybe if you don't want to do an extra step and figure out what to do with that 2, we can just plot 2y versus t squared. That's allowed. Now our slope of that straight line is going to be our acceleration, just like we were asked. When drawing a line of best fit, use a ruler. Have as many points above the data as below. To calculate line of best fit, do not use data points. Use points on the line of best fit. indicate the points you use by drawing a triangle on the graph. That little triangle right there. You cannot learn or get better at physics by watching videos. Get off of here. You have to solve hundreds of problems. Good luck. Questions in the comments. Let me know if it helps, or I should not have done this.